Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on stability. You know, the whole idea is when the column reaches the critical load, without a warning, it buckles. That is where the stability problem becomes very critical, and you need to find out the critical load. If you don't know that, then you will have surprises in your structural response. And how do we handle a problem related to stability to start with? Mathematically, even though we have said we are going to live in small deformation, in order to investigate stability, you take the beam as bent. Okay, that is very, very important. And when the load reaches a critical value, without a warning, it buckles. Buckling can happen in a column like this. It can happen in a beam. It can also be precipitated by a shear. And in all these cases, what we have done is we have deliberately taken this as deformed, and only when it is deformed, we are in a position to take an element. You get an extra term that I have the compressive load separated by a small displacement delta V. On the other hand, when we analyze a beam for deflection, we have consciously taken this as undeformed configuration. You get the point? That is the fundamental difference. When we did the deflection analysis, we did not consider the beam as deformed. We solved it in undeformed coordinates. On the other hand, when you come for buckling, we consciously take that as a deformed, then only we are in a position to write the mathematical expression. And first we have looked at the fixed free, that is a cantilever, then we moved on to pinned column, and actually pinned column forms the basis. See, if you look at the critical load, I have also put this as P star, that is equal to pi squared E I minimum divided by L squared, and all the other cases are compared with this P star. And you know, the boundary conditions are very easy to write, because I have a pinned joint, I have x equal to 0, V is 0, at x equal to L, the V is also 0, and in both the ends, your bending moment is 0, which in turns out to be d squared V by dx squared equal to 0. Even though I have written EA d squared V by dx squared, you should see that as d squared V by dx squared, as simple as that. And what we did was, we got the governing equation, and we did not solve, we directly took the solution from your mathematical analysis, and then you simply take the V as C1 plus C2x plus C3 sin lambda x plus C4 cos lambda x. I have 4 constants and I have 4 boundary conditions. So, we had the enough data to proceed, and we wrote the, when we substitute the boundary conditions, you get these expressions. See, this is not in one order. Okay, so you have to figure out, that is also a good reason why you have to apply your mind to unravel this. For problem to problem, it is slightly different. Intentionally it is done so that you are alert. And in order to have a non-trivial solution, I need to have this determinant go to 0. That gives me an expression wherein I get the critical load as n squared pi squared EA by L squared. You have multiple equilibrium positions possible, and when I have n equal to 1, I have the mode 1, which has a buckling shape like this, pi squared EA by L squared, and when I have n equal to 2, I have P2 as 4 pi squared EI by L squared. That means if I increase the load, you are expected to get that mode shape. In practice, you will have to, do something. This is the point where it crosses 0. So you have to make this as 0 externally. Only then in buckling problems you will see that. I will also show you in an experiment what we have done. So what you find is as n increases, you have different equilibrium configurations. The column cannot remain straight. That's a understanding that we get out of it. So the critical load is the least one, pi squared EI by L squared, and it is better to recognize I as I minimum when I have non-circular cross section. In a circular cross section, every diagonal is having same value of moment of inertia, and it can have buckling in all the 360 degrees. Okay. And once you solve this, you get the displacement as C3 sin lambda x, and I have also mentioned you are not in a position to calculate the value of C3. It is indeterminate, it mainly because we have linearized the governing equation. The moment curvature relation was non-linear. In deflection, we said we are going to live with small deflection, we can ignore the second order effects. Same approach we have followed in buckling also. In fact, if you consider the non-linear relationship of moment curvature, it is possible for you to evaluate for a given load what is the coefficient C3. If you look at the buckling problem, what is more important is the value of the critical load. How the buckled shape is of secondary importance, because the functionality of the column is disturbed. So primary importance is to get the critical load, and we also do not have the mathematics to investigate what happened once the critical load is reached, because the deflections are very large. And this shows experimentally I can get the mode 2, but I have to do something to do for the inflection point. I have to make that, only then I will be in a position to see that. Sometimes you will see I have such beautiful curves, you will wonder, can a column which looks so strong otherwise can have a shape like this? In order to bring and drive home that point, we have got this experiment done and it has come out beautifully. Next we move on to fixed pinned column. What is the difference? Only in the boundary conditions. And you have already seen what way to handle a fixed end, what way to handle a pinned end. So it's a question of the equations having a different form, that's all. And you have to simplify them. Okay, I leave that as an exercise, but I will show you the final results. You have the boundary conditions like this, and this is the solution we start with. When you substitute it, as I have told you that this is not in an order, so you figure out whether the equations are correct. That's also an exercise for you to see that you have followed what is done in the class. And as we have seen earlier, for a non-trivial solution, I need to have this determinant go to 0. See, what happens is we have handled a fixed free, that's a cantilever. The equation was simple and straightforward. When we looked at pinned pin, the equation is also very simple. But once you come to any of fixed pinned or fixed, the equations are little more complex and you will have to apply your mind to solve it. So what I am going to have this is, I am going to have this to go to 0. You have to recognize this should be translated into tan square root of p by EI L should be equal to square root of p by EI multiplied by L, and this needs to be solved. Okay, one can solve it easily in a graphical method or analytical also you can solve. And when you solve it, this happens to be a value 4.493, and it's inconvenient to look at as this number. We'll also simplify it. So, the critical load is obtained as 20.19 EI by L square, which is approximated as 2 pi squared EI by L square. See, I have an ultimate objective. We are going to take pinned column as the basis. From the length of that column, we will also visualize the length of other end conditions. See, buckling is one problem where the critical load drastically changes because of the end conditions. Fine. And in reality, how do we have these end conditions realized? We will also have a discussion on that. And from that point of view, if you want to compare, rather than looking at this as 20.19, it is convenient for us to have this as 2 pi square. Okay. Because pi squared EA by L squared is your basic expression. So, I can say what is the value of the equivalent length of the curve. And once I go to the reflection curve, it's a very long expression. Please make a note of this. I have this as V equal to C3 multiplied by minus square root of P by EI into X plus sine of square root of P by EI into X plus tan square root of P by EI into L multiplied by 1 minus cos square root of P by EI X. See, from your notes, you should have all these deflections. Don't make an attempt to remember this. It's not a learning on memorizing your capacity. Okay, you have to have a physical appreciation. In all buckling problems, what is very important is the expression for the critical load. Because deflection, you have to also appreciate that you have a deflected shape of this form. It's of secondary importance because the column has lost its ability. That's what we are concerned about it. And here you see, when you compare to the pinned column, it's able to take twice the load. Fine. The critical load means I can increase the load 2 times. Only then buckling happens. That is the physical appreciation that you should retain in your system. When you look at a pinned fixed column, you should feel that it is safer than a pinned column. Okay. Then we move on to fixed column. And once I have a fixed column, you will all recognize that you will also have slope 0 at both the ends. So, the boundary condition is like this. All of this we have looked at even when we discussed the principle of superposition. When we wanted to have a deflection, we have recognized that you have a fixed end, you have a pinned end, you have a free end. We have learned how to write the boundary conditions. So, the boundary conditions still remain the same, but the governing equation is different. The governing equation also, what way we have obtained? We have deliberately looked at in the deformed configuration. This is the only problem in this course where we write the governing equation by looking at the deformed configuration. So, that is a fundamental difference in the basic analysis here. So, once I have these boundary conditions applied to this expression V, I have the 4 equations. Here again, the sequence is not in the same way that I have given the boundary condition. So, you figure out and also alert me if there are any typographical errors. Fine. And for a non-trivial solution, I should have this determinant to go to 0. So, when I do this, I have an expression like this. Tell me what way I should translate this into a condition for me to find out the critical load. See, when I have the determinant, I get the expression this determinant should go to a value 2. Can you look at what way we can impose this condition? Can you Just read the equation. You all have mathematical ability to recognize this. When will this expression go to 2 in a simplistic manner? So, this goes to 1 and this should go to 0. So, I should illustrate the condition as I should have sin square root of p by EIL equal to 0 as well as cos root of p by EIL equal to 1. Earlier case we had sin lambda L equal to 0, fine, that was only one condition, we solved one problem. But now I should have both of this go to a respective values as indicated. So, this is possible when I have p by square root of p by EIL equal to 2n pi. The difference comes only there, otherwise the mathematics is simple, straightforward. Only when you look at the determinant, final expression, how do you represent it in a convenient form for you to get the critical load? The focus is to get the critical load. So, from this I can easily find out the critical load. So, I have the critical load as 4 pi squared EA by L squared. So, look at, if I have a fixed condition, the column is very strong, 4 times the load it can withstand in comparison to a pinned column. That is what is shown as 4 p star here, and p star is defined as pi squared E I minimum divided by L squared, because I have taken a rectangular cross section. And here again, if you look at the equation of deflection curve, very similar to what we saw in fixed pinned, and if you look at closely, only this term changes. You write down the complete expression. I have V equal to C3 multiplied by minus square root of p by EIX plus sin square root of p by EIX plus tan square root of p by EI multiplied by L by 2. All of this multiplied by 1 minus cos square root of p by EIX. So, that is only a small difference between what we saw in fixed pinned and fixed. And what is significant here is the critical load is very high. That means you can be a little relaxed when I have good end conditions. And just observe the animation. The animation is very nicely done. It will drive home the point, how the columns are relatively placed in terms of critical load. Fine, you have a visual representation, and now I am also going to provide a excellent summary. So, in the case of clamp to free, the basic expression we had was when the determinant goes to 0, cos square root of p by EIL equal to 0. So, that gave me p critical as pi squared EA by 4L squared, and you could also get the deflected curve as V equal to C1 1 minus cos lambda x. When we went to pinned end, we had sin square root of p by EIL equal to 0. This gave me p critical as pi squared EA by L squared. See, in all my expressions I have just put I, you must recognize that it should be I minimum, which is done in the diagram but not in these expressions. So, recognize that you should put this as I minimum. So, when we moved on to fixed hinged, I get the governing expression as tan square root of p by EIL equal to square root of p by EIL. This should be satisfied. From this I get the critical load, which we rewrite as 2 pi squared EA by L squared. And in the last case, the condition was I should have sin square root of p by EIL equal to 0 as well as cos square root of p by EI multiplied by L equal to 1. So, this is satisfied. I get the critical load as 4 pi squared EA by L squared. In all these cases, you have the deflection also. It is a very nice summary of what we have discussed so far. At a glance, you get what happens, and visually you see what is the shaded region. If the shaded region is the longest one, then you have the strongest column, okay, and it is all compared with respect to the pinned end. See, now the question comes, why do we have a pinned end as a basis? See, if I have a pinned end, it can easily rotate. See, only in your course, problems are posed that this support is pinned, other one is pinned free, other one is fixed free. If you are asked to go and look at the real structure, you will have to idealize depending on the constraint in the problem as one of these supports. So, now what I will do is, I have two holes, okay, I suppose you are able to see two holes. I have put the one pin and I am able to freely rotate. What do you say as fixed end? It should not rotate. Fine. Suppose I put another pin, probably you can see this better. I have two pins and I am trying to rotate. See, the pin is not of the same size as the hole. Suppose I have the pin of the same size, I am able to have some rotation. That is because the pin is diameter is smaller than the hole diameter. Suppose I have a properly made pin, even this rotation is not possible. Looking in other words, when I have even two pins, it prevents rotation. Okay. That means if you want to idealize this as fixed end, you are also justified, even though you make a small error. So, in reality, you do not know how the constraints are. We always do the boundary solutions. That is, I will have upper bound and lower bound. I will do the analysis as pinned and then get one number. I will also repeat the analysis with fixed. I get another number. So, between these two I should operate. See, that is how engineers work on. See, even though in this course we have seen support conditions, we have also looked at to what extent these supports modify your results. In fact, while we discussed the reflection problem, we had a truss. In fact, it was a frame. It was fixed at one end, the I-beam. We calculated considering that as a pin joint and then calculated what is the deflection. We calculated again the same problem with that as fixed. The difference was about 2.5 or 2.7%. Fine. Why that was done? See, in your rigid body mechanics, it is sacrosanct. You should know when the symbol is given that is pinned joint, put the boundary conditions appropriately. When it is a fixed joint, put the boundary conditions separately. But all that is indicated by a, we had symbols for that. You will not have symbols attached to practical structures. While learning the course, you need to have those symbols for you to appreciate the different joint conditions. When you come to field practice, there is always a dilemma whether it is a pinned joint or a fixed joint. Fine. And we have also seen in certain applications, the end conditions are not influencing much. Definitely in the case of buckling, it has a significant importance, but it is a favorable direction. And you have this, let us go back to this Euler buckling again, because when we started this class, you may not have observed certain nuances very closely. So, what I have here is, you look at here, as the load is increased, suddenly it buckles, okay, without a warning. That you should recognize. That is why buckling is so important from analysis point of view. And what you find is, it causes the column to loosen its stability. That is, the introduction of the slightest lateral force will cause the column to fail by buckling. See, I have always been showing experiment and also analytical justification and also numerical justification. And one of the difficult experiments to be conducted are buckling experiments, because the problem is, the slightest lateral force can come from imperfections in the material the column is made of, how the column is made of. That is very difficult to model. And we have also said that we have a elastic continuum. That is how we have developed the mathematics. So, Among the several experiments, costliest experiments are buckling experiments. $1 million have to be spent in making the specimen appropriately. And also the deviation from experimental observation and analytical calculation are maximum in buckling experiments. Please understand that. Fine. When you do your experiment, you find the deviations are there, don't get annoyed, because you cannot make anything perfect, because the analytical model wants a perfect specimen. Perfect specimen is extremely expensive. Okay, it's not in 2-3 orders, its order of magnitude is very, very high. Fine. And we have also said that this is credited to the genius, mathematical genius Euler, and we have also looked at, he had physical difficulties. With all that, he was able to do it. So, you look at the deflected shape, and I have already said these are experiments indicative of the relative merits of the capacity to withstand the critical load, because you can see the weights put. See, if I have to perform the experiment in an idealistic manner to get the critical load, I should have provision to vary the load, I mean, in a manner continuously. The loading system what I have shown is not all right, because I have discrete loads. These discrete loads may miss the critical load. Fine. And what we have also seen is, even if you go beyond the critical load, you will see a deflected pattern so beautifully in your experiment, your analysis may be difficult. That is different. And I have also used this to show another aspect. We have discussed that what you have as these positions are neutral equilibrium positions. Fine. And when I redo this, you can recognize this has already buckled. This load is higher than this. Here you can see in a subtle fashion, and you can see that in a definite fashion here. I have one equilibrium position, I apply load, I have another equilibrium position, I apply another load, I have another equilibrium position. So, these are all neutral equilibrium positions, but transition from one to another is sudden. So, it loses its stability. Okay. And I said whether buckling is useful or not. People have used it in your toys. People also have used it in electrical switches, where you have snap buckling is used for making positive contact. Okay. I am now going to discuss the concept of equivalent length. Okay. So, I take the pinned column as a basis. I call this as LE equal to L. I can also visualize, see, if I have a longer column, it is dangerous. A shorter column is better. That is the way you have to look at it. Longer the column, its tendency to buckle is more. Its tendency to buckle is more. If I go to fixed pinned, we have already got the expression. Now, we are going to have a relook from a different perspective. I call this as LE equal to 0.7 L. Okay. And if I have a fixed, it behaves like half the length of the pinned column. Okay. Suppose I have a cantilever, it behaves differently. It behaves as if it is twice the length of this column. That means it can have only the least load of critical load. This will have the highest critical load possible. So, another way of looking at a column problem is, look this in comparison to a pinned column, what way you can visualize the length of the other columns. So, when from the point of view of critical load, the boundary conditions are very significant. In other problems what we have looked at, the boundary conditions, you can get the lower bound and upper bound solution. You can also do the same thing for buckling also, because physical problems do not have the symbol attached. You have to go and find out from the constraints to idealize, and true fixed conditions are always difficult to simulate. And you also have another concept called slenderness ratio in column buckling. And what you do is you write the moment of inertia as A r squared, where r is the radius of gyration. So, instead of looking at that as a critical load, I can also get that as critical stress P by A. I have pi squared E by L by R whole squared. So, L by R is a slenderness ratio, and if L is larger and larger, the column is more flexible. So, that is what is said, slenderness ratio is a measure of the column's flexibility. You do not want that to be flexible. In a structural application, you do not want that to be flexible, you want that to be strong enough to withstand the load. Fine. And are there other applications? I have always gone beyond the basics of the course to motivate you to see what all you can learn in future. See, use of buckling as energy absorbers. Thin walled tubes are extensively used in aerospace and automobile industries as energy absorbers. The most important phenomenon of axial crush tube is to absorb and convert larger amount of kinetic energy into plastic strain energy. During progressive crushing, lobes form sequentially and it is subjected to large strain without any material failure, because the idea is to protect the occupants. See, you also have metallic foams. That is another way of softening your crash victims. Okay. Another way is to use thin-walled tubes. So, it is of importance to study this phenomenon in detail for crash-worthy design. And you see this beautiful animation. You see how this is crushing. This is done by one of my students who did his masters in IIT Madras. It is an excellent piece of experimental and numerical analysis work, and you could quickly see what are these dots. Do not say defects. DIC. See, I have said you have to be current students, and digital image correlation is the rage now. Once finite element was a rage, everybody was hanging on to it. In experimental mechanics, everybody wants to learn digital image correlation, and this is an excellent candidate for doing digital image correlation, because I am going to have ultra high strains of 30%, and DIC is highly applicable for large deformation problems. And you should guess from this experimental setup, I have two cameras, and that is the reason why I brought this. I want to sensitize you that you have this, and I also have another way of looking at it. This is from the numerical work, which shows how the square tube has buckled, and this is plastic buckling. See, material has not separated, and this is what? This is happening at 10 millimeter per minute. Now, what I am going to do is, I am going to increase my speed of rate of loading, and I have said rate of loading is different, and look at how beautifully the patterns develop. Okay. Do not you think this is very, very interesting? Isn't it? So, that means the crash tube is doing its job very well in absorbing more and more energy. So, you can be protected. Like engineers, future engineers, you have to develop all of this, fine, for passenger car protection. I think you can see the animation again. This is so interesting to see. See, what is peeling off is the paint that is put for image correlation. Image correlation, because the paint should be adhered to the surface very well, because it is an aluminum tube. Some places it is too smooth, so it is not adhered. And not only this, see, my students have always compared numerical as well as experiment. Very few labs across the world do these comparisons. Only when you compare, you burn your fingers and you understand you are modeling correctly. And look at here, this is a non-linear finite element analysis, and this is a digital image correlation. Look at visually, the patterns are quite identical. And this is a very, very complex problem. It is a non-linear finite element analysis. It is not a simple problem to handle with. Okay. So, this should give you motivation. What you have learnt as strength of materials only is basics. They are very, very important. Fundamentals are very important. And you have to graduate and solve very challenging and complex problems of today. So, that requires your training in a numerical technique as well as an experimental technique. Okay. Then in this course, we have also looked at extensive use of photoelasticities to understand the concepts related to stress. That advantage even the developers did not have. They had done crude experiments. This is a subject which developed based on experiential knowledge. It's not theoretically done. And wherever possible, I have emphasized where there is a deviation. And when you are looking at shear stress, there are many places where you can ignore, but you cannot ignore near the load application point. Near the load application point, your strength of material result of parabolic variation is absurd. The shear variation is very, very high just below the boundary, but on the top surface it is still 0 because it has to satisfy that free surface requirement. And these stresses are comparable to your bending stress. So, failure can happen unless you strengthen this. When you are doing the design, strength of material helps you away from the zone, okay, away from the load application and end conditions. You have solution from strength of materials. But even that, was it right? We have also looked at, you can actually take a photograph if you want, because they have very nice beautiful patterns. You don't get them anywhere. You don't get them anywhere. That is the reason why I thought that I should have it here. I have this uniformly distributed load. When uniformly distributed load, strength of materials, was it right in all respects? I have also pointed out where it was deviating. Okay, we will see that. We will see that. What are the two quantities I showed? It's again very important. This is correction to sigma x. It's no longer varying linearly. It is non-linear. And you also have in addition, there is sigma y. Can you see from the pattern existence of sigma y? Or your eyes are sensitive enough, tuned to that? You look at what happens at the bottom, you look at what happens at the top. Do you find there is asymmetry here? The fringes are well developed here, fringes are not fully developed. Okay, see, you see beyond this red some slight shade of color coming out. The width is broader, the width is shorter. Okay, you have to be sensitive. The experiments reveal truth. Please understand. You may make certain simplifications for the purpose of your analysis. You may say curvature is linear. Experiment recognizes this as non-linear. You may say shear stress is small. Experiment recognizes even that small shear stress and throughout the experimental pattern in tune to that. There are no approximations in an experiment. So, you should do a careful experiment and interpret every aspect of the experimental analysis. Don't ignore. Don't come out and say the experiment is 30 years old, so I see unsymmetry and then walk away. Like in your history books, what each king has done, he has planted trees on either side of the road. Same answer for every king. Have you not done that in your history in the schools? Okay. And whenever you find deviation from experiment and your mathematical analysis, one of the blame is on the equipment, not on the performer. The performer has to be careful and systematic in performing the experiment. These are the usual ways people wriggle out of real challenges. Okay. And I have said only in buckling experiments, even when you do a careful experiment, the deviations are very high because you cannot get a perfect material. You cannot have a perfect cylinder. You can't have a perfect sphere free of defects. So, they are all very, very expensive. We have seen this for simply supported beam. We have also done it for a cantilever. So, when I have a cantilever with a distributed load, you should anticipate with a pinch of salt, strength of material is reasonable for you to accept. but theory of elasticity will always say other quantities. Okay, but they are second order effects. I have also put not to scale. Okay, that means this is very, very small, but you should recognize that there are deviations. Okay, and when I have a tip load, I have the fringe pattern like this. Now let me change the conditions. Fine. Suppose I have this as a propped cantilever, that means one side is fixed. Look at the change in the fringe patterns. For all of this, what do you use? You use your Flexure formula. From that point of view, Flexure formula is a success. Okay, but look at all the nuances and the small changes are captured in the experiment, and you find beautiful patterns. Okay, see, if you look at this is like a cantilever, this is like a fixed beam. Okay, you see combination of both, because when I change the end condition, so it also gives you an appreciation of why we want to look at for different end conditions. From a mathematical analysis, we should understand what is happening. In a physical system, if you look at these end conditions, you have to apply the engineering acumen to model it. Only then you become a good engineer. If you keep solving problems, somebody has coined it as fixed support, somebody has coined as pinned support, is not going to make you as a good engineer. You should know what are the limitations. If you come across the limitation, how to wriggle out of it. So look at and get the lower bound result and upper bound solution. Suppose I have this as fixed. In all these cases, you will have this variation. Okay, because when I have a distributed load, I am compressing it deliberately, and you will see the symmetry. Asymmetry is seen here. I could see orange color here. I could not see that orange color here. Is the idea clear? So the experiment recognizes the presence of sigma y. Just because analytically you cannot handle that, we have simplified it. Because the error introduced is small, we have ignored it. As a designer, what way we could accommodate this? Go and have a careful factor of safety. Is the idea clear? So we accommodate it as practicing engineers at some part of the analysis. We don't ignore it. If you ignore it, you will have surprises like bridge collapses after a few days of inauguration. Fine. So these are all very beautiful patterns that you have, and the end conditions are changed. And I have also emphasized, I said that I can have a fixed end, but just by two supports. And I also felt that some of you have to go and definitely see my engineering mechanics, the discussion on force systems, equilibrium, and also move the force from one point to another point. You have to master it. If you master that, then you have a better grip of the subject. Because I say in a simplistic manner, a load is applied. How this load is applied, if you look at, I have to take a pin and then pull it like this. If you look at from a side view, it will be like a pin resting on a hole. And then if you go and look at it, we make several modeling steps. All that is taught in your rigid body mechanics. If some of you have not looked at it carefully, please go and have a careful look at it. So when I have a pin, you always have deformation. Even though in rigid body mechanics we say it is rigid, you have deformation, you have force interaction, and this force interaction is elliptical distribution. Okay, this is done by Hertz, and you model this as by a resultant, okay, as a single concentrated force, and then you replicate this concentrated force as along the line, then take an equivalent value, then use principle of transmissibility and move it to that point. So a simple problem where you have a end load which is put like this, when you physically translate, it has many things aspect added to that. So transmissibility of force, you can move the force along its line of action. When you want to move the force from one point to another point, you have to recognize you have a force as well as a couple. If you understand this, your bending is simple, torsion is simple, and engineering analysis is very, very simple. So, in this class we have looked at stability in a broader perspective. We have looked at different end conditions affecting the critical load. We have also looked at equivalent column length and discussed about slenderness ratio, and also we had threadbare discussion. How do you physically approach a problem? The physical systems do not have the end conditions marked. As an engineer, you have to go, depending on the constraints, idealize it as a pin joint or a fixed joint, and fixed joints are very difficult to build in reality. And if you have a dilemma, always do two analysis, get lower bound solution as well as upper bound solution. Then I have also said, in order to motivate you to take interest in solid mechanics, there are very interesting challenging problems that are beyond this course, which really makes human life much safer in the new emerging challenges. Thank you.